Hello, this is Mr. Craig, and I want to talk about resonance today. And I'm well aware that we haven't talked about the mechanisms involved, but I'm just giving a real brief overview today. So, want you to read over what I have written there about resonance and resonance hybrids. But I do want to remind you about formal charges. Remember that formal charges are going to be very, very important for just about everything that we do in organic chemistry. So, just to refresh your memory on how to figure out if a formal charge is correct, I know that many of you remember actually the rule where if you have carbon, nitrogen, oxygen, fluorine, that carbon to have a formal charge of 0, or the nonmetals in that column have 4 bonded pairs and no lone pairs. Nitrogen will have 3, or group 5A will have 3 bonded pairs, 1 lone pair. In group 6A, typically oxygen, 2 bonded pairs, 2 lone pairs. And halogens, typically fluorine, but it could be a lot of those, 1 bonded pair and 3 lone. So that's the real quick way of being able to figure out formal charges. But now we're going to take a little bit of an adventure with these resonance, and we'll have to actually calculate formal charges quite a bit this year. So remember or recall, I'm not sure which it would be, that we have to first find out what the assigned value is. And the assigned value is determined by taking half of the shared electrons, those are the bonded electrons, and then we're going to add it to the lone electrons. So, for example, if I'm looking at this oxygen here, so again, we want to look at 1/2 shared. So the shared are these electrons. And if it's a single bond, then that means that we actually have 1/2 of 2 electrons. And then when I look at the lone or the unshared electrons, then I've got 2, 4, and 6. And so those 6 will be added on. And in this case, my assigned number of electrons for that singly bonded oxygen is 7. And then the second part of this is to actually determine the formal charge is to take the valence number of electrons, which is from the group number that it's in. So remember, 4A has 4 electrons, 5A, that's nitrogen, has 5 valence electrons, oxygen 6, and then the halogens have 7. And so you'll take your valence number of electrons and subtract that from your assigned value that you just did up here. So in that case, if I'm looking at the formal charge calculation, I'm going to take for oxygen, it's in group 6A, so it has 6 valence electrons. And then I'm going to subtract that from what I just found. And in this case, it gives me a -1 charge overall. And that's why you see this negative charge listed here. If I look at, say, the nitrogen, okay, let me erase those. If I look at the nitrogen, you have to ask yourself, okay, well, we need to do the assigned value. And the assigned value, let's see, what color did I use up there? Red. Okay, so the assigned value is 1/2 shared. So looking at this nitrogen right now, you've got 2, 4, and then 4 more, because again, there's a total of 4 electrons in that. So the nitrogen here has 8 shared electrons. So that would be 1/2 of 8, which in this case, there are no lone electrons on this nitrogen, so that'd be +0, would give me an assigned value of 4. Then you take to find the formal charge again, you take the number of valence electrons minus the assigned number. So in that case, nitrogen is in group 5A, so 5 minus 4 gives me a +1 charge, and that is why we see that +1 there. So what we're going to need to do is keep track of how many electrons we have in our structure, how many are shared, how many are not being shared. And that's going to be pretty instrumental in doing these resonance structures, as well as a lot of things that we're going to do for the rest of the year. Now, I don't want you getting hung up just yet on this combined resonance structure here that I have on the right. This is the reality. Again, we spoke back in AP Chemistry about finding bond lengths. And this is just representing that this is the average of what's happening. And recall that these electrons are moving back and forth between this oxygen and that bonded pair, and then it comes back and then it does the same thing there. So I don't want you getting hung up over the combined, I think I called it, the combined representation, because we're not really going to be asking you about that. We're going to just look at the different resonance structures. So I don't care about the combined. I put that on there just mainly for kicks and giggles. But let's take a look at the first problem that we have here. So flip the page over. And unless it's one of your polyatomics or something that I think you could probably figure out, I would give you like the structure. This is the bare bones structure. I want you to like put it together. And notice that the only charge that you see on here is for this carbon atom right here. So everybody else should have a formal charge of 0. And so to expedite the process, you should be able to say, okay, well, I know that carbon wants to have 4 bonds and hydrogen wants to have a single bond. So looking at it like that, my carbon has a formal charge of 0. So now I got to work on my oxygen. So oxygen wants to have 2 shared pairs and 2 lone pairs, but we can see that it's connected to a carbon. So I'm going to put a carbon here and a hydrogen and a hydrogen. Yes, there are only 2 hydrogens on this compound. That's why it has a +1 charge. Here, let me clean that up. So if I go back and I look at the oxygen, for oxygen to have a formal charge of 0, it should have 2 lone pairs as well. 2 shared pairs, 2 lone pairs. Then when I look at the carbon, in this case it has, let me highlight them, it has 1, 2, 3 pairs of electrons, which is a total of 6 shared electrons. And that's how you have to say it to keep yourself from going crazy. So if I have 1/2 of 6 electrons, plus there are no lone electrons on here, okay? So that means 0. So now my assigned value is 3. Ask yourself, where's carbon at on the periodic table? Well, it's in group 4A. So my formal charge calculation would be 4 valence electrons minus the 3 gives me my +1 charge. And so that is why there is a +1 here. Okay, so that is the original structure. Now, keep in mind, resonance means that it's going to shift. Now, it's not so obvious here because typically when we talk about resonance structures, we're talking about a double bond that's moving around. And I'll be honest with you, this is going to be probably the only singly bonded scenario that will turn into a double bond and then go back to a single bond that you'll see until we start talking about mechanisms. So I thought I'd start off ugly early here. So when we look at this resonance structure, what's going to happen is, I didn't put a note on here, but the electrons always move toward the positive charge, okay? I don't think it was that I stated that in the example or in the explanation, but electrons always move to the positive charge. And obviously, electrons would move away from the negative charge. So when I look at what's happening here in a resonance structure, so I'm going to start here. Actually, I'm going to copy just to speed things up here. I apologize. I know you have to write all this. Okay, so I'm going to put this over here. And so what's going to happen is I'm going to now take this double bond or this pair of electrons and move it here. And so that pair of electrons is now going to go away. As a result, by moving that pair of electrons, actually I should represent it over here. I apologize for that. We're going to move it this way. And by doing that, I'm going to now create a double bond. And you're probably looking at that saying, well, okay, the carbons have 4 shared pairs, which they want to have a formal charge of 0, but now the oxygen just has this pair of electrons and nothing else. So if I were to do a formal charge calculation for the oxygen, again, we want to look at how many shared pairs do we have. shared electrons. I got to remember to say that. So we've got 2 plus 4 more. So 1/2 of 6 plus there are 2 lone electrons here. So that gives me a grand total of 5. And then, so that's my assigned. I can't abbreviate this, sadly. So then what I want to do is I want to take and do the formal charge calculation, which in this case, it has 6 valence electrons minus 5, which gives me a +1 charge. And so now to finish this off, I'm going to put the +1 over here on the oxygen. So technically that is my resonance structure resonance structures for this compound. And don't forget that we definitely want to put brackets around here. And you don't have to put the charge on the outside because the charges are indicated here. Now, I know that you see that there's a double arrow here. How do we get this back to the way it was? Because that's what resonance does. It'll take that, here, let me move this. It'll take the pair of electrons and move it back to the oxygen. So now we have an oxygen with 2 lone pairs of electrons, and the carbon, again, is back to 3 shared pairs. I know it's kind of fun, kind of wacky, but that's how we go on it. All right, let's take a look at part B. So taking a look at part B, we're going to do the same thing here. I'm going to draw out my skeletal structure based on this. So I've got my carbon, hydrogen, hydrogen, and then a carbon. I'm going to put the double bond down here in hydrogen. What I want you to notice is that in this case, we have a carbon with a negative charge. So I'm going to put the negative over here. So if I look at this as is, I can tell that this carbon on the right has a formal charge of 0. I need to finish putting electrons here on the oxygen to give it a formal charge of 0. The hydrogen, obviously, since it's a single bond, has a formal charge of 0. But now I've got to focus on how can I get the carbon to represent a formal charge of -1 in this case. So remember that if it's the assigned, we have to figure out the assigned value for this. So what I'm going to do is I'm going to look at it as it stands right now. So if I were to do a formal charge calculation, I want to do the assigned, which is first, and that would be 2, 4, 6, and 1/2 of 6, 1/2 of 6 would give me, and there's no lone pairs, +0, would give me 3. And I know that carbon's formal charge, the number of valence electrons is 4. So if I did this, that would give me a +1 charge. So that means that this number here needs to change. And so by looking at the negative charge, I'm going to have to put a pair of electrons here. If I do that, let's now recalculate and see what this value is. So the single bonds remain the same, plus I have 2 electrons. So 1/2 of 6 is 3 plus 2 gives me 5. And then if I have 4 minus 5, that plus charge changes into a negative charge. So now I have my structure drawn correctly as represented up here. All right, so let's get rid of the calculation down. Oop, not that far. Nope, don't want to get rid of that. So let's erase these. All right, so I have my structure. And so what's going to happen is, just like I said a second ago, if you have a negative charge, that means the electrons move away from the negative. Okay, so what's going to happen in this case is that I'm going to take this pair of electrons and I'm going to make it from a lone pair to a double bond. So let's redraw this. Actually, let's recopy it here. Copy, paste. Okay, so now what I'm doing, let's erase that. Okay, so when I move that pair of electrons over, I'm going to get rid of that. I'm going to form a double bond. that means that that negative charge goes away. So what happened? In this case, the carbon here on the right now has 5 bonds. It cannot have 5 bonds. We all know that carbon can only have 4 shared pairs. So what has to happen is that one of these pairs or shared pairs needs to move. So we're going to put those electrons somewhere around the oxygen, not necessarily up there, but change that to a single bond. So in this case here, when we move that pair of electrons over, and when we moved it over, we now have created a formal charge on the carbon back to 0. However, what has happened to the charge for the oxygen? Here, let's move this over. I don't like the look of that. Okay, so now oxygen, as we all know from doing many, many formal charge calculations, that the oxygen now possesses a -1 charge. So we can see that the movement of the negative charge went from the carbon here on the left actually to the oxygen over here, because the double bond went from, let's use a different color. Ooh, that's ugly. Went from here to here. So it's still, that double bond's moving around that carbon on the right. So if I were to draw my arrows correctly here, let's do that. So if I want to show the motion that is happening here on the left, I like that. Let's erase this cat. And so to get it back, then this, we'll say that pair of electrons, it doesn't matter which one, is going to move, and then it's going to cause that reaction to go back to the single bond here. All right. Hope that makes sense. It'll get easier, I promise. Don't freak out by looking at this first set of problems. The letter H, I'm gonna let you figure out what's going to happen, but I'll give you a heads up. One of those oxygens has a double bond on the carbon where the other one does not. And remember what that 2 at the bottom there means when it's in parentheses. All right, well, hope this has helped. I know it's as clear as mud now for you, but it's been fun.